Okay. Hi, everyone. My name is Ashlynn Vick, and this summer I was mentored by Dr. George, and we were investigating TIDE or testing intermittent devices for energy harvesting. To start, I want to share with you about a long-term acoustic data set. In 2015, the Monterey Bay Research Institute installed an underwater microphone or hydrophone on a deep sea ocean observatory platform near the coast in California. Since it was near the coast, the researchers were able to power it using a 32-mile long cable for power and data. And this hydrophone listens to underwater soundscapes. So, for example, marine animals, earthquakes, ships, and other events. The impact of this data is that researchers can observe for long periods of time to understand ecosystem changes and also human impact on marine life. In this project involving coastal deployments, existing seafloor sensors require cables for power and data because of the proximity to the coast. However, if we want to investigate remote deployments or locations that have been unexplored in the ocean, places that are not near the coast, the system must instead harvest energy from the environment, or what we would call ambient energy. We would need a system that harvests energy to power itself by storing that energy and using that energy. And so some potential energy sources come from related projects at FAU from previous REU students. And these projects deal with ambient or environmental energy. And so on the left, there is a tank filled with water, and it contains several benthic microbial fuel cells, which harvest energy from sediment or the ocean floor. And on the right, there's another tank with a piezo cylinder that captures sound energy from acoustic waves. These projects demonstrate that useful energy can be harvested directly from underwater environments. However, energy sources from the environment are often irregular and unpredictable. So, for example, this figure illustrates a common characteristic of energy harvesters, that their power outage changes as the surrounding environment changes. So in the blue, it's showing that, first, this is a soil microbial fuel cell. So the researchers flooded a tank in the blue so that it would have a lot of moisture. So that led to more power outages, or led to an increase in power output. But then in the yellow, when there was drought periods, there was less power output. And so this demonstrates the challenge that environmental energy harvesters do not produce a constant amount of power. And so whether the energy comes from microbial fuel cells or acoustic sound or other ambient sources, the available power fluctuates over time. Because harvested energy is not continuously available, the systems also need a way to store that energy for future use. In this project, we will store energy in a supercapacitor. We use a capacitor because they can charge quickly, and also they have the opportunity to recharge millions of times. And this differs from traditional batteries, which may have maintenance costs associated with them, especially if we're planning to deploy them in deep sea environments. It might be costly to repair or replace them, and also you might disturb the environment doing so. So this motivates our project for this summer. We would like to understand how batteryless systems store and use energy. And so this slide illustrates the overall pipeline of our system and how we can follow energy through each stage. So as I mentioned before, some ambient energy sources were acoustic sounds or the fuel cells. In this project, we stuck with, or we limited, or our scope was the analog discovery, so a more controlled environment, and that's what we used for this project. And this emulates our ambient energy. This feeds the green board, which is our energy harvester. This is a board from Analog Devices. And so it takes in small millivolts of voltage and it boosts it so that you can charge a supercapacitor. It also regulates that voltage so that you can power the rest of your system. As we said before, our energy storage is going to be a capacitor. The sensor for this project is a temperature sensor. And in order to process our findings, the red board, that is our microcontroller, the MSP430. And we chose this microcontroller for its ultra low power capabilities. So it has several low power modes that we can use. And we like these low power modes because they eliminate the CPU usage and some system clocks so that we consume less power. When we use energy in our battery system, we want to see how the stored energy responds to these different operating modes from the breadboard or the microcontroller. And so this brings us to the test scenarios on how we use energy. For this project, we use the low power mode 3 as our baseline because it is the lowest power mode that still supports periodic sensor sampling. So this still keeps the clock running while making sure that the CPU stays asleep. This makes it an ideal baseline for comparing the energy costs of additional workloads. So the additional workload would be in the second scenario where we're actually logging data. So when we're just in the baseline, we're not logging anything, but when we're in the middle box with direct memory access, we are logging data. So in this box, we use direct memory access to directly take our temperature sensor readings and store them in memory. And we use a timer that samples every 35 milliseconds or so to take that temperature sensor reading and store it in memory. And then in the third block, that is an even greater workload because now we want to intentionally involve the CPU to do calculations. And for this one, it is still in low power mode 3, it's still logging, and then now we're calculating temperature statistics every 13 seconds when we want the CPU to trigger. Oops. These three operating modes represent increasing computational loads, and understanding how each workload affects stored energy helps us to determine how long our system will stay powered on in the event of power loss. This brings us to our characterization tests and results. Since we know energy harvesting is intermittent, we want to know how long our battery's operation can stay alive in the event of power loss. The three testing scenarios mentioned before are increasingly costly with their workloads. And so the way that this pipeline worked is that I charged the capacitor with the green board and the capacitor up to 3.6 volts. That was a threshold. I then disconnected input power to simulate a power loss. And then we monitored the discharge to another threshold of 2 volts. And then while we're doing this, we're collecting data. And so we ran this test for the three operating modes, the baseline, the DMA only when we're just logging, and then DMA plus CPU when we're logging and calculating temperature statistics. And so the data shows that low power mode 3 has the longest runtime of 520 seconds, which comes out to about 8.6 minutes. And then meanwhile, the DMA and CPU has the shortest runtime with about 470 seconds. Then if we look at our bar chart on the right with the power, it's a corresponding relationship. So we can see that the low power mode consumed the least amount of power while DMA and CPU consume the most amount of power. And so this is telling us that in low power mode, your capacitor is discharging or draining slower, while if you're running it with DMA and CPU, you're draining the capacitor faster. In conclusion, in this project, we characterized how long a battery sensing system can operate using stored energy. We also showed how increasing computational workloads reduce runtime because they consume more power. Going forward, we would like to replace analog discovery, our controlled environment, with a real intermittent sensor energy or real intermittent energy source like the acoustic transducer we mentioned earlier, or the fuel cells in other previous RE projects. We'd also like to revisit adaptively storing energy by adding a network of capacitors. So the image on the right shows a lot more capacitors than we use because I only used one. But in this project called Stash, they assigned a capacitor to each component. So a capacitor for your MCU, a sensor, a backup capacitor. And the idea of this is that you would hopefully extend your operational time. And of course, by adding more capacitors, we would hope to rerun the same test to make sure that we are still logging data. And so ultimately extending batteryless operation from minutes, as I recorded, to hopefully hours or weeks will enable long-term monitoring of remote underwater environments. By making this possible, we move closer to continuously monitoring remote and possibly unexplored regions of the ocean. And so this impact means that researchers can better understand marine ecosystems and how they are changing over time. Of course, I would like to take time to thank my mentor, Dr. George, as well as his students, Gabriel and Felipe, for assisting me this summer. I would like to recognize NSF's support and also thank FAU for hosting our cohort this summer.